Thank you very much. I want to thank the organizers for this beautiful conference and thank you all for coming. So the idea of this talk to talk about some problems which we are interested in extremal combinatorics, to give you the taste of these problems, and more importantly, to explain why maybe we find them interesting. And of course, I don't expect any specific knowledge in combinatorics, so if I don't explain, I try to define most of the things. But if I don't explain something and you don't know, please stop me and ask questions. So let me start by saying that the following general phenomena is behind many mathematical results, and it says that every large system, chaotic it might be, contains a well-organized subsystem. Actually, paraphrasing Theodor Motzkin, complete disorder is impossible. Although I think when you read today the news and see what's going on in the world around us, you strongly disagree with this statement. Nevertheless, in mathematics, this phenomena appears in very high generality, and here is a list of various areas where you can easily find this phenomenon. Now, once phenomena is established, the next natural question is to ask which well-organized substructures we can find, and obviously how large should be the original system be to contain such well-organized substructures. So now this is a very central theme in the area which I'm doing, extremal and probabilistic combinatorics, and today I want to show you this phenomena on the example of restricted subgraphs of H-colored graphs. Okay? So let's start with a basic definition. The edge coloring of the graph is proper if it contains no two edges which are incidents which got the same color. Right? So this is a very basic notion in graph theory. So you see the coloring there, right? The edges which share a vertex should get distinct color. But if you see it first time, maybe one important example which I want you to keep in mind for the duration of this talk is this Cayley sum graphs. This would be very useful. So imagine you take your favorite abelian group, you take some subset of elements in this group, S, and then you can define a graph in a very natural way. Two elements of the group X and Y are adjacent if X plus Y equals to S. And observe that the nice thing is that this graph is already edge-colored, because in addition to defining edge XY, I can immediately color by the element S. And because it's a group, so first of all, this would be a abelian group, this would be a graph, and because it's a group, this coloring would be proper. Obviously, at every vertex, all X plus Y for different Y would be distinct. Okay? Now, I said that I want to look on restricted subgraph of H-colored graphs. So what kind of restriction we are going to look? So we will want that these subgraphs we are trying to consider will have some colors appearing uniquely. Okay? So if, say, all colors appeared uniquely, we'll get this notion of rainbow subgraph. So for example, this cycle is rainbow, it's colored, because every color appeared uniquely. And so what I want to do in this talk, I want to discuss the following question. So you have a large graph coming from certain family, and it's important you consider an arbitrary edge coloring of this graph. The only condition is that it should be proper, right? Edges at the same vertex cannot repeat color. And then you ask which fixed subgraphs I can find in every such coloring in such a way that they are rainbow. Okay, so that would be the theme, and I explain you why we care, right? So again, you will have a big graph coming from certain class. It would be edge colored for you by adversary. You have no control on the edge coloring, but you want to say, despite that adversary colored the graph properly, I can find something, and this something is restricted, the colors appear uniquely. Okay. So actually, the study of this problem has a very long history going back to Euler to 18th century, where Euler studied Latin squares. So Latin squares are really cool objects. So you take n by n square, and you fill every row and column with numbers 1 up to n, such that every row and every column contain all the numbers. And these are very natural objects, so we probably the most natural for us, we know them from multiplication table of finite groups. So take finite group, take multiplication table, you get a Latin square. But they appear also in other areas, like if you like Sudakov, the field Sudakov is a Latin square design theory, and so on. When we have a Latin square, the important notion is that of transversal. Right? Transversal is a choice of one square in every row and column, which in addition contains all different numbers. So in particular, so this is in the green, you have a transversal, okay? And so what Euler actually cared about was the following question. So he asked when, for which n, you can construct a Latin square which you can fully decompose into disjoint transversals. Right? So obviously you have n squares, so transversal has size n, you should have n transversals when you can construct such a Latin square. Actually, the story is really cool. So why Euler got interested in this problem? So he was back then in Russia, and he was at the court of Empress Catherine the Great, and there was a puzzle which was floating at the court about 36 officers. I can tell you this puzzle in the break if you're interested, and it was very much related to the work Euler did. So actually the answer for this puzzle would be the existence of this very Latin square for n equals 6, right? 36 officers, okay? So here is decomposition. For example, this Latin square which I draw for you, it's actually decomposable into 5 disjoint transversal. You see them in a different color. Another way to say this problem, which is very appealing, so what actually Euler was interested in, he was interested in so-called or pair of orthogonal Latin squares. So imagine you have 2 Latin squares. They would be orthogonal, that when you superimpose them, obviously now every square has 2 numbers. There are n square squares, and so they're orthogonal if these pairs of numbers exhaust all n square pairs, right? So these 2 Latin squares are orthogonal if you get all n square pairs, and you can easily see that if you have a Latin square which is decomposable into transversal, it's exactly equivalent to the existence of orthogonal Latin squares, because what I can do, given this Latin square, can construct another one. So I take this green transversal, but now instead of putting numbers from 1 up to pi, I put all 1s there. And then I take the yellow one and I put all 2s, purple all 3s, blue all 4s, and say white one all 5s. I will get another Latin square because these were transversals. You can check. It's a legitimate Latin square. And then when you put them one on top of another, you indeed get all n squared different. So this is much more appealing version of the problem, okay? But of course, by now you should ask, this is a very nice combinatorial problem, what it has to do with the edge coloring. And actually the connection is pretty straightforward. So imagine you have a Latin square. About every square here you can think as an edge in complete bipartite graphs, right? So one side of this bipartite graphs are your columns, another side is a row. So for example, square B1, it would be the edge connecting B and the point 1. And so what we get, if we take all the edges of the complete bipartite graph, we can use the numbers of the, which are written here, and use numbers as the colors, but you think that maybe red is 1, yellow is 2, green is 3, and blue is 4. So you can take all squares of red color and put these edges here and color them red. And similarly, you can do with blue, green, and so on. So what you get, that Latin square is completely equivalent to complete bipartite graph, which is properly edge colored using n colors, right? Because every row, every column should contain all different numbers. And so what actually transversal corresponds to, right? So actually this Latin square does not have full transversal. We'll talk in a second about this. So I draw you partial transversal. So these are 3 squares in different row and columns and contain different colors. It corresponds to a rainbow matching, right? So therefore, starting transversal Latin squares corresponds to starting rainbow matchings in a proper NH coloring of complete bipartite graph. And we can say Euler equation as follows: for which n we can construct a proper NH coloring of the complete bipartite graph, which we can decompose into rainbow magic. Okay? And you remember, so the original problem came from Catherine the Great, and the interesting question was whether for n equals to 6 we can construct such a square. Actually, Euler himself managed to construct such a coloring or orthogonal Latin squares for all n which are 2 mod 4. Which are not 2 mod 4, which are not 2 mod 4. He actually didn't know the answer for question for 6. And the question for 6 was solved much later by Tari in 1901. And the whole problem of Euler took 180 years to solve, where eventually Boyce, Parker, and Schrinkande in almost in 1960s constructed orthogonal Latin squares for all other values except 6. Actually, it's very interesting. You can Google it, so when they solve it, this solution makes the front page of New York Times. So there is a New York Times issue which has that thing, okay? So disjoint, right, so you cannot use the same square twice, right? You find the one transversal, then the next transversal should use a different set of squares. Or in terms of matching, you find me one matching, the next matching cannot use these edges. It should use a different edges. Yeah? You decompose your structure, right, piece by piece. Vertex, of course, right? So we're only talking about edges, right? That's a very good question. In all this talk, disjoint means edge disjoint. Very good, okay? Now, to finish the story of Latin squares, let me mention a recent spectacular work by Richard Montgomery, who solved one of the oldest problems in this area. And let me get back to this square. Right? You see, this Latin square does not have full transversal, but it has full transversal whose size is n-1, one less than the full transversal. And there was an old conjecture about Latin squares by Reiser, Brawl, and Stein, who said that every Latin square, there's nothing special about this thing here, contains transversals of size at least n-1, either the full transversal or the size n-1. It's actually very interesting. You can check that even multiplication tables of groups do not always have a transversal. So if you have a cyclic group whose order divisible by 4, if I'm not mistaken, you will not get a transversal. And so indeed, this conjecture was recently proved by Richard Montgomery, a quite spectacular result. Okay. So now, any questions so far? No, for large n, right? So we don't know, right? It's like all these proofs which are a bit probabilistic. They have element like that. We don't know it for small n, and they start working with the n, which are sometimes reasonable. If they use what David mentioned, regularity lemmas, then n is very unreasonable. But if you use only probabilistic methods, then n is reasonable, but still very large to do the exhaustive search. Okay. Now let's go back to restricted coloring of graphs. So a very basic concept in the graph theory is that of cycle. And there is a very basic result which says that if you have n edges, you should contain a cycle. Right? It's very easy to see that the largest acyclic graph has n-1 edges. So you can ask, what if I have an edge-colored graph and I want a cycle which is a bit special, which has certain restriction? So as I said, restriction for me would be that certain colors appear uniquely. So let's start with a very basic restriction. One color will appear uniquely on a cycle, right? So I want to ask how many edges your properly edge-colored graph should have to guarantee a cycle with one edge appearing uniquely. So again, graph is given from some family, just number of edges which matters. Coloring is adversarial, you do it. But I want to say that if your graph has many edges, no matter how you color it, I will find a cycle, and the cycle will have a unique edge. So in particular, in this case, you see blue is unique, okay? So to see that this is already an interesting question, I want to start with an example which shows that the answer is no longer linear, okay? So here is a construction. You take what we call in combinatorics binary cube, or if you want, we take a group Z2 to the K, we take, as a vector space, we take a standard basis of this vector space, and we take a Cayley sum graph with respect to the standard basis. So if you remember, my vertices are all binary vectors of length k. Two are connected if their sum gives modulo 2 standard basis, and moreover, the color of this H would be I. Okay? Now, let's do several observations about this coloring. So first of all, observe that if you go along any cycle and you look on the color, they correspond to the vectors, this vector should sum up to 0 modulo 2, right? Because if you do u plus v and then v plus something, when you add it, v cancels, right? So if you take edges along the cycle, right, the colors, they correspond to some of the pairs of elements, they sum up to 0 mod 2. Because this is a basis, there is non-trivial linear combination, which is 0 mod 2. So in order it would be 0, every color should appear even number of times. So there is no unique color. So this indeed, this coloring does not contain cycle with unique color. We have 2 to the k vertices, this is our n, and we have k times roughly 2 to the k edges, because from every vertex the degree is k, so we have n log n edges, right? And as I said, that there is no cycle with unique color, okay? So the first result which I want to mention is that this result is tight. It's indeed the best possible bound. And indeed, about 20 years ago, when we started looking at these problems together with Peter Kivash, Dhruv Mubay, and Jacques Verstraete, we proved that every graph with, say, 2n log n edges, which is properly H-colored, will always contain a cycle. Moreover, this cycle would be logarithmic lengths, which has H of unique color. Okay? I mean, it might look for you, okay, some nice combinatorial problem. Why maybe you should care? So in order to see that it might be interesting, let me give you a different way to look at this problem, which actually has application to theoretical computer science and coding theory. Okay? So one interesting notion in coding theory or in theoretical computer science is this notion of even cover. So you have a collection of sets, and I call it even cover. If you look on the ground set, they cover every vertex of the ground set even number of times. So the way to look that it would be more coding theory, you take a characteristic vector of the set, which means a vector whose length is the size of the ground set, and you put 1 on the elements of sets and 0 otherwise. And if you add this characteristic vector, your family is an even cover if these vectors are linearly dependent. Their sum is 0. Okay? So even covers are very natural generalization of cycle, because cycle actually in every graph is even cover, right? The degree of every vertex is 2. They also correspond, imagine you have a system of linear equation mod 2, then even cover corresponds to linearly dependent subset of equations. And therefore it's a natural equation here. If I give you a collection, and let's say for today's talk, all sets will have the same size, k, and I'll tell you that you have m sets, I want to know what is the smallest even cover you can find. So for example, if your k is 2, it's a famous Gauss problem. So you're asking what is the shortest cycle in the graph if I tell you the number of edges. For general k, it also corresponds to a very central question in coding theory, which connects the equation of rate and distance, right? You can think about the sets. If you put these vectors as a column of parity check matrix, then the even cover is and you take a linear code defined by this matrix, just the kernel. Then the even cover tells you the shortest vector, okay? So this motivated Uri Feige about 15 years ago to conjecture what is the answer for this question. So the way maybe to parameterize the answer, let's agree that we're trying to find, say, an even cover of size L or a linear dependence of size L. And then the question, how many k-element sets or how many vectors with k-ones we need? And the answer is here. You don't need to kind of digest the formula. I can tell you from where it comes. It's n times n over L to the power k over 2 minus 1. And it really comes by looking on a random collection of that many sets. And you can show that if you take this M much bigger than this quantity, you will have even cover of this size, just first moment computation, and otherwise you don't. Okay? The important thing, the motivation for URI was that it came from a random constraint satisfaction problem. It's a very central problem in computer science. I give you an instance of some hard problem, say 3SAT, or some other constraint satisfaction problem. You know that if instance is dense, it's not satisfiable. The question, can you prove it to me? And if you want to even, I'm not even saying algorithmically, but just you want to show me something inside your 3SAT or inside your problem, which once I see it, right, it doesn't matter how fast you find it, I will know that it's not satisfiable. And this is very closely, intimately related to this. I will not go into this. Now, this conjecture was recently solved by Goswami, Kothari, and Monohar, at least of some logarithmic factors, but the original proof was quite heavy. In particular, they needed some results from eigenvalues of random matrices, something called non-commutative Hinchin inequality. And what I want to show you is that how this simple result about finding a cycle in an H-colored graph with unique color can give you a very short solution for this problem. I think the shortest is when k is even. When k is odd, you need to work more, but with k is even, it gives you a very short solution. But again, just remind ourselves what we're proving. So you have some number of k element sets. Maybe you make out of them characteristic vectors, right? You have some number with precisely k1s. This is a number, and you want to show that there is a linear combination of roughly L of them, which sum up to 0. Okay? And I want just to kind of illustrate this would be there is this very famous saying that every talk should contain one joke and one proof. So this would be my proof, right? I want to show you this result. Okay, so it will fit just in one slide, and to make it easier, let me take my k being 4, right? So again, my setting is I have binary vectors of length n. Every vector has precisely 4 ones. I have, here the formula is even nicer, n squared over L of them, roughly with some log. And I want to show you that there are L vectors which sum up to 0, and this L is the optimal answer for this problem. Okay? So how we will going to do this? So we are going to build a certain Cayley sum graph. As I said, this would be an important notion for this talk. So my vertices would be all element subsets of my universe, right? So these are my vertices. Or think all binary vectors with precisely L1s. And I connect two sets by an edge. If the symmetric difference is a 4 tuple, which is in my family, right? In particular, you see they need to have intersection here of size L minus 2, and the symmetric difference should be my 4 tuple. The other way to think about it, if I add these vectors modulo 2, I get a characteristic vector of 4 tuple from the family, right? This is precisely Cayley sum graph, where these are the set of generators. Now observe that once I have this Cayley sum graph, I immediately can color it by the color of this 4 tuple E, right? So I connect S and T if they are addition modulo 2 is V, okay? Now, the only thing which remains to do is to use this lemma which I mentioned. So let's count how many vertices and edges this graph has. So first, maybe before I'll go to it, I want to stress that observe that this is a proper coloring, because this is an equation. When you know your vertex S and you know the color E, it's uniquely determined another vertex which is connected to this vertex S by color E. So therefore, you can solve it from this equation. So it's indeed a proper coloring. Okay, and now let's just count the things. So the number of vertices in my graph, I denote it by capital N, is n choose L, right? Because I take all L element subsets of N. Now, how many edges it has? So let's count the edges. To get an edge, I first pick L minus 2 elements, which is this intersection, and I add to it the element of this 4 tuple to get this picture. So it's n choose L minus 2 times the number of 4 tuples, And you can trust me, I mean, you can see from here, this is n to the power L minus 2, this is n squared, so this is roughly n to the L, and you have here almost L factorial, 1L is missing, so if you look what this number is, it's precisely, I cook it to be this 2n log n, which will guarantee me a cycle with a unique color. Perfect. So, and moreover, I know that the cycle is logarithmic, and log of this number is precisely L log n, right? So it's exactly what I want. Log of n, it's L log n. And so the last thing to see why I care that the cycle had a unique color. So observe the cycle means you have a bunch of sets S1 up to Sk, such that their characteristic vector give me one of the four tuples from my family. And important that one of the four tuples is unique, appears only one. So now you have these equations. Obviously what you can do, it's a cycle. So Si appears twice on it. You can add it modulo 2. So when you add it modulo 2, obviously on the left-hand side you get 0 because Si appears twice. So you're doing modulo 2, you get 0. And here you get some of characteristic vectors of some four tuples in your family. Now obviously this thing could be also identically 0 if every element appears twice or even number of times. But here is the catch that we know this cycle had a unique color. So one of these EIs appear only once. So therefore this is really a non-trivial linear combination exactly of size L log n, which proves your result, right? So this is a kind of a convenient way to use this result, which gives you a short proof for something which before took quite an effort. Any questions? Now let me continue. Now, once you know the answer for finding a cycle with unique color, obviously, yeah. Oh. So this is what proof does. Actually, we don't know how to remove this very good question, this extra log factor. The conjecture is that you can. If k is odd, we know how to improve it. Again, using this machinery of passing to an edge-colored graph and using some, finding some cycle with unique color. But yeah, this is a very nice question, and we don't know how to deal with it. Otherwise, it would be very, very clean solution. Okay, so the most natural question, once you know it, is what happens if you want fully rainbow cycle? And indeed, when we started this problem, we thought, okay, that was our motivation. We just couldn't solve it, right, in 2006. But our conjecture was that n log n edges is already enough to guarantee you a fully rainbow cycle. So if you again take a graph with that many edges, any coloring, as long as it's proper, you get a rainbow cycle. So this conjecture is still open. It appears to be harder than we thought, like almost 20 years later. We know two results in this direction. The first result we prove with Oliver Janzer, which is kind of a strengthening of this thing with one edge. So we can actually prove that at that density, you will have a cycle which is essentially rainbow. Almost all the edges will have unique color, but not quite all, right? So this is the first result. And then there is recently a very, very nice result by Alon, Bukic, Sauerman, Zakharov, and Zamir, which came very close to proving our conjecture. They have extra log. So they know that if you start with n log log n edges, you color the graph properly, you get a rainbow cycle. Okay, so now let me again digress and tell you why this might be interesting in the other areas. So to do this, I need the notion of dissociated sets. So you have a group, you have a bunch of elements, and then I tell you that there is no non-trivial combination of these elements with sign plus minus 1, which equals to 0. I don't assume that my group is abelian, but just it's convenient for me to write it with plus and minus. So this is a dissociated sets. Now it's immediately should ring a bell for you. It looks a little bit like independent set of vectors in vector space. And indeed, there are. So these are actually things which appear naturally in harmonic analysis and additive number theory. And indeed, yes? The order matters, and I only allow the exponent plus minus 1. Right. But no matter how order you take, you will not get a non-trivial Exactly. And so this dissociated set indeed plays a role, the same role as independent set for vector spaces. So maximal dissociated sets are spanning. And you can even prove that for the same, they don't need to be really the same size like in vector spaces, but one can prove that they're almost the same size, all the dissociated sets. And motivated by that, Schoen and Shkredov define a dimension of the group by the size of the maximal dissociated set the group contains. Right? You give me a group, then, or actually, sorry, even a subset, right? Not only the group. So you give me a subset of the element of the group. Not necessarily we need, right? Like in vector spaces, we can take a span, right? The subset of the element of the group is a maximal, the dimension is the size of the maximal dissociated set it contains. Okay? Any questions? So this is a definition. Now there is a very big theme in additive combinatorics. You take a subset of your group, you add it to itself, and you observe that it doesn't grow. Then you want to say something about the structure of the set. And your intuition is that if the set plus itself doesn't grow, it's not much bigger than the original set, then it behaves in a sense like a subgroup or maybe like a subspace in vector space. Okay, that's a very general theme, extremely important. There are many, many results in this direction. So therefore, if we believe this intuition, right, if I have a thing which is very close to a subset, and imagine my subset is over finite field, say GF2, then the dimension of this set should be logarithmic in its size, right? So that would be the intuition. And indeed, such results were proved. So there is a theorem which says that if you have subset of the group such that A plus A has size proportional to A, then the dimension of this set is at most logarithmic in A, right? For any abelian group. And then for non-abelian group, we know it almost logarithmic. And this is result by Alon, Bukic, Sauerman, Zakharov, and Zamir. Okay, and what I want to say, I will not bother you with another proof. If you want, I can tell you in the break. To prove the first result, you can use precisely this lemma about finding a cycle with one unique color. And to prove the second result, you can use the second result of Alon, Bukic, Sauerman, Zakharov, and Zamir about the existence of rainbow cycle. You can really reduce it by defining an appropriately H-colored graph, and by now you have a good feeling. When you have a group, you look on some graph or some other Cayley graph, and you suddenly get a graph which is colored, and any information you can get, and cycle is exactly this linear dependence. Any questions? Okay. Good, so if you look, I will get the entire result. And actually there is another problem which I can attack using this thing, is the problem in coding theory called locally decodable codes or locally correctable codes. There are several problems which are really amenable to this tools, and there are some results we can get using this technique, but this is for another story. Yes, absolutely. Now, if you lost me by now, it's a good time to kind of recharge. So I'm changing again the direction. So, so far we talk about matchings, like Euler's problem and Latin squares. Cycle, now I want to talk a little bit about trees. And actually now it's exactly what David mentioned in his talk. So I want to talk about global problems, which are a bit harder than the local ones. So we would be talking about finding nearly spanning subgraphs. And therefore, right, even finding a trees is already quite challenging. So to tell you this part, let me a little bit relax the type of the colorings I'm going to look. So before, my coloring was proper, which means at every vertex, I allow unique edge of each color. Maybe there would be no red at all, but if red appears, only once. Now I will define K-bounded coloring, where I always think about this K being small, say 1, 2, 3, where at every vertex, I allow at most K edges of each color, right? So it's a very natural extension of proper coloring. So you have a coloring of the graph where at every vertex you allow at most K edges of each color. As I said, observe that one bounded coloring is a proper coloring. And now the graph which I'm going to color would be complete graph. You would say, okay, complete graph is such a boring and simple object, but once you color it, right, you remember, I completely not restrict your coloring. Coloring you chooses. You get a really complicated structure, right? You can take complete graph, you can color it arbitrarily. I even not restrict you to color with a minimal required number of colors. Coloring can be anything as long as it's, say, proper or k-bound. And the question I want to address, what kind of trees I can find in such a coloring in such a way that now they are rainbows, that every edge of the tree has a different color, okay? And again, as usual, now I maybe before presenting the result, I actually change the order. Let me first motivate this problem. Let me first tell you why at all maybe you should care, okay? So the first result which I want to mention, or the conjecture, come from the area of graph labelings. So graph labelings is a very general area where you try to assign to the vertices of the graph labels, which typically elements of some group, in such a way that certain restrictions would be satisfied. It very naturally appears in coding theory, in construction of networks. And the particular problem which I want to mention is the following. You have a tree, you have an abelian group, and you want to assign the element of this group to the vertices of the tree such that this labeling is harmonious, which means if you sum the labels along the edges of the tree, they should be all distinct. Okay? So this was the notion which was introduced. Is it clear? Right? So you have a tree, group, assign the labels, the sum along the edges should be distinct. And there is a beautiful conjecture of Graham and Sloan, which saying that for every tree and a group on n vertices and a group Zn, there is always a harmonious label, right? So basically you can use as few elements as you need, right? You want to give the labels to n vertices, so good to have at least n elements. So that you have group Zn, and you can do it for every tree. Now, observe, if you didn't thought about it, there are many trees on n vertices. There's a famous Cayley theorem from 19th century, which says that there are n to the power n minus 2 different labeled trees. And actually, even if you don't care about labels, it's more or less the same number. Typical trees don't have so much isomorphism. And so for all of them, this should be true. Okay? So right here is this, for example, harmonious labeling. So this is 3 on 7 vertices, right? And I added for you these numbers, modulo 7, and you see they're all distinct. So what we know about this conjecture, okay, as usual in combinatorics, people start and check it for some very specific trees. I don't know, pass, there is some trees called caterpillars and so on. The conjectures appeared quite difficult because, as I said, the abundance of trees. So even an asymptotic version of this conjecture was not known. By asymptotic version, I mean you give me, instead of group Zn, you give me a slightly bigger group. Let's take 1 plus epsilon times n. So you have some slack. I want to assign elements to the vertices of trees such that all sums along the edges are distinct. We didn't know it in general. The only thing we knew was that if you assume in addition the tree has bounded degree, then this is true. Right? Observe that in particular, this will come maybe in several results. So the trees can be very complicated. In particular, it have some very low degrees, but very high degrees, right? So, for example, you can have, I don't know, some really big star, and then some matching, and then again some big stars, right? Something like that. So as long as I would know that such thing does not exist, the degree is really bounded by constant, that new and asymptotic version. Okay. You this problem because this problem is very intimately related to the question I asked, right? You have a coloring of the complete graph, proper coloring, and I want to find a certain tree in this coloring appearing rainbow. And here is a connection, right? So you take a complete graph on n vertices, you take all elements modulo n, and you take some Cayley sum graph according to the set of elements. Or simply you take your n vertices and you color the edge between x plus y by x plus y modulo n. Okay, so this is not a very general, this is a very, very specific proper edge coloring of the complete graph, right? You agree? So x plus y modulo n is distinct for every x, so it's a proper coloring. Now imagine, right, so here is this, right? So for example, 1 and 3 would be colored blue because sum is 3, 7 and 3 would be colored blue because sum is 3, 6 and 4 would be colored again 3 because it's modulus 7, it's 3, and I can color the full graph. So you have this coloring, right, based on the sum, and you have this tree. And actually this harmonious labeling of this tree, I produce it from this connection. And the connection is that if you find me your tree, your favorite tree, in this coloring of the complete graph, which is proper, in such a way that tree is rainbow, it exactly means these assignments of label the vertices of tree is harmonious, right? Because you see, right, rainbow means exactly because of how we construct the coloring, that the color of this edge, this sum is different from this, from this, from this, from this, and from this, right? So in particular, if I knew to show you that every coloring, proper coloring of the complete graph on n vertices will contain every tree in a rainbow fashion, I would prove the Graham's-Long conjecture, okay? Now let me mention another problem which comes, any questions, right? So here connection is pretty straightforward. If you think a little bit, that's exactly what you want to do, but still observe, you even want to do it not as general as I originally hoped, not every coloring. You have a very, very specific, nice symmetric coloring, and even then it's not clear how to do it because exactly your structure is very global. Now the next problem which I want to mention comes from the area of designs or graph packings, and it's a very famous conjecture of Ringel. So what Ringel said is the following. So take a complete graph on 2n minus 1 vertices. The complete graph on 2n minus 1 vertices, right, has 2n minus 1 choose 2 edges, which is 2n minus 1 times n minus 1. So then Ringel said, pick your favorite tree on n vertices. So this tree on n vertices has precisely n minus 1 edges. Again, arbitrary, there are exponentially many trees, anyone should work. What he claimed is that you can tile the edges of the complete graph using the copy of your specific tree. Like any tree of correct size, right? Of course, the tree has n minus 1 edges, 3 on n vertices. So you should be able to put 2n minus 1 copies of this tree inside your complete graph, completely disjointed, right? So to cover all the edges. Okay, so very beautiful conjecture. In the beginning, when I first saw it, of course, by then there was some evidence, mind-boggling, right? Except for the numerology, you don't have any good evidence why this would be true. But here is an example. So we have K5, and my tree is very simple, path of length 2, and here is a decomposition, right? So I decompose the edges of the K5 into path of length 2. Okay. So again, what we know about this conjecture? So again, we check it for various interesting trees, paths, stars, caterpillars, and so on. So here we have a big success some number of years ago by Jost, Kim, Kuhn, and Ostus, who proved this conjecture for all bounded degree trees. So it's again, this seems that if trees has bounded degree, it makes problem a bit easier. So you give them arbitrary bounded degree tree on n vertices, n minus 1 edges, and they can tile the complete graph using this tree. Okay. Now here the connection to rainbow problem is much harder to see. It's actually not at all obvious. It was not done by us. It was already known in the literature soon after Ringel's conjecture, but it's very beautiful. So here how you can think about this problem, okay? So here's your favorite tree. I draw it here as before. You have 2n minus 1 vertices. You put them on a circle, right? So think about your complete graph, the vertices appear on the circle, right? Now, all edges are present, but I want now to color them. I think that all edges are connecting these vertices present, so let me color them based on Euclidean distance on the circle. Right, so all vertices which are in distance 1 will give me, say, green color, right? And observe that this is in this case is a cycle. So the degree of this cycle is 2. So therefore it's 2 bounded coloring. I allow you at the vertex 2 edges of green. Now I take distance 2, right? And this would be my color blue. Actually, it's not one cycle, it's a union of 2 cycles. But again, obviously, the graph is too regular. The blue color has degree 2. The coloring is still 2 bounded. Then I have vertices of degree 3. Again, I introduce new color. And I connect the vertices of degree 3. And the last, because my n is 2n minus 1 is 9, my n is 5. I get the red color, right? So this is my picture. And observe that the number of colors is precisely n minus 1, right? You have 2n minus 1 vertices. Of course, I take the shortest Euclidean distance. So the distance is from 1 up to n minus 1. So again, it's good to notice that also I'm interested in arbitrary coloring. You as adversary provide me this coloring. This is extremely specific to bounded coloring. But imagine in this specific 2 bounded coloring, I managed to find you this tree, which I draw you there, in such a way that it's rainbow. Then I claim that we will know to prove Ringel's conjecture. Moreover, we will know to prove it in quite elegant form. So I will just take this tree and I will rotate it clockwise, right? And observe, so let's go back. Observe that, for example, this green edge, because the way the coloring will move to a different green edge. So these copies of trees would be indeed disjoint and in a different, and you basically exhaust by rotating your tree along the cycle, exactly 2n minus 1 times as you need it, you get your decomposition, right? So it would prove even stronger result, which people suspected at the time because of this connection, that you can find one tree and then just rotate it around to get this decomposition. So again, this motivates to look on this problem. And indeed, we looked together with my 2 co-authors, Richard Montgomery, whom I already mentioned, and Alexei Pokrovsky, and it motivated us to prove the following rather general result. So what this result says, you have a complete graph on n vertices. You give me an arbitrary k-bounded edge coloring, right? So if k equals 1, you give me arbitrary proper coloring. If k equals 2, this is a Ringel, you give me 2 bounded coloring. So you give me arbitrary k-bounded coloring on, of complete graph n, kn. Then you give me arbitrary tree of size n over k, slightly smaller. We need a slack. Say 1 minus epsilon n over k, right? And the theorem says that I can find you this tree in this coloring in such a way that the copy of your tree is rainbow. All edges have distinct color, right? Right, again, arbitrary k-bounded coloring, arbitrary tree, right? And very important, we don't have any restriction of the degree, only of size slightly smaller than n over k. And then I can find this tree rainbow. Now, a couple of comments in place. So first of all, as we said, if you take k equals 1, then I claim that I can find you nearly spanning tree, any nearly spanning tree rainbow, which gives you the asymptotic version of Graham's long conjecture, right? This will give you, in particular, if you apply to very specific coloring of the complete graph, it will give you the harmonious labeling for this tree. If you take k equals 2, you remember this was our Ringel's coloring, then very specific Euclidean coloring, then you get an asymptotic version of Ringel conjecture, which will tell you that if your complete graph of size 2n, roughly the tree of size n will pack. Now it's not packed, but it covers most of the edges, okay? The proof is heavily probabilistic, right? Maybe you again will have question if I know it for all n. No, I definitely don't know for all n, but it's reasonable. So again, it starts with some reasonable numbers. I only use some concentration inequalities, martingale, some analyzing some random algorithms. It's actually some algorithmic procedure how to embed it. It's really important also to mention that in such a full generality, this error term is needed. So in particular, I can construct you a coloring of the complete graph where I cannot find a rainbow spanning path, right? It's not very difficult because of certain coloring would come from groups. Certain group operation will not allow me to have it. So this error term is needed, Okay, so in that sense, it's a tight result. But to finish my talk, let's go back to Ringel's conjecture, right? Ringel's conjecture was asking us something a bit weaker. It wasn't an arbitrary two-bounded coloring. It was a very specific, very nice, very symmetric two-bounded coloring. So therefore, in this coloring, obviously, maybe this error term is not needed, and we conjecture that it's not needed. And indeed, we revisit this problem with Richard and Alexei some number of years later, and we managed to prove for that specific coloring that we can embed any, right, so I a bit changed my parameters, so now the number of vertices is 21 plus 1, so the tree has n edges, any NH tree in this coloring in such a way that tree is rainbow, and in particular this proves Ringel's conjecture. And the way we did it is, so we started with our original result where we can embed almost a tree of right size, and we used a different technique called absorption technique. And actually here it's a very versatile technique, going back to works of various people, Rodol Ruchinsky in particular, which does the following. So if you do your embedding in certain way, typically it works very well if you do it random in some way. So you don't destroy the original structure of the coloring much. And therefore, once you're done, you can look on the remaining vertices and try by doing various switching, by trying like a very deterministic procedure to attach them to the, say in this case, it would be almost tree of size n, and I can attach the remaining vertices to this tree in such a way to get fully rainbow tree, right? And that's how we did it. I should say that there is a different proof by now of Ringel's conjecture, which was obtained by Kivash and Stade. Okay? And since we have a lunch and I shouldn't stay between you and lunch, let me stop here.
Thank you for the great talk. Any questions?
Like you have a beautiful result about proving the small linearly dependent set or small even cover exists. Yeah. Have you ever considered the time complexity or like efficient algorithm to find the even cover?
So our proof, this is a very good question. So our proof of this basic lemma is pigeonhole. It's not algorithmic. So the way to show that there is a cycle with unique color, so the procedure is not very difficult. You count a certain rainbow path of certain rainbow lengths, so rainbow path of certain lengths in your graph, right? But since the length is logarithmic, it would be hard to enumerate, right? You need to think if I know how to enumerate. It doesn't look to me that this is algorithmic. And then I find the number of this rainbow paths, say of length n, log n, is a lot. It's much bigger than n squared. So therefore I find two vertices, put the same endpoints, between which there are many rainbow paths of length k. If this number is bigger than k factorial, it means that the colors on this path cannot be repeated. And therefore I take two of them, and I get a cycle with unique color. So it's actually very nice. The whole proof of the result of even cover, I can do it in 2 pages. Just first prove the lemma and then to show you the second color. But I need to check if I can maybe do dynamic programming to do, but I would expect that maybe not. Right? So not so efficiently.
Thank you. Yeah, the questions? Can you tell us about the puzzle that you mentioned at the beginning of the talk, since you have time?
Puzzle. Yes. So actually, it's precisely about, so what the court of Catherine the Great was the puzzle. So you have 36 officers, which come in 6 groups. They belong to 6 different regiments, and they have 6 different ranks. And the question is, can you arrange them in the kind of, so maybe they need to guard something, into 6 different commands, such that in 6 different combination, such that in every group there is officer of every rank coming from every regiment. And if you think about this is precisely you're asking whether you have a Latin square, 6 by 6, right, which you can decompose to 6 disjoint transversals, right? And that was what made Euler to think about this. And of course, I'm not sure how true this story is, but that's a legend, which
Thank you.
appears.
Are there other questions? If not, then let's thank the Sudakov again.